My name is Renu Raman Sahu, and today we will be discussing the assignment of week 6 and some of the previous year problems. So let us go to the first question. So here the question is asking about uh, the free energy of a ferromagnet close to the transition. It is given, and it has the form F naught plus A naught T minus Tc, and what we have to T minus Tc m square plus B m to the power 4, and F naught, A naught and B are positive constants, and m is the magnetization, T is the temperature. So what we have to find is to find we have to do uh, what we have to do is to find a relation between m square and T. Okay, so the way to do that is uh, to find the minimum of the energy with respect to the the magnetization m. So what we do is we take the derivative of f with respect to m and set it to 0, and whatever the expression comes m versus t, we will see that would be your option, that would be your correct option. So let us do that. You are able to see the screen? Yeah. So what the first question says is the free energy of a ferromagnet close to the transition, it is given by this formula, and here F naught, A naught and B are constants, and we have to find the relation between m square versus T. So what we have to do is to find where the energy gets minimized. Okay, so it is dou F by dou M is equal to 0. This is what we need to find. So how do we do that is we have the expression for m. So let us take expression of f as a function of m. So f naught plus A naught T minus Tc m square plus B m4. So dou f by dou m is equal to A naught T minus Tc times 2m plus 4bm3, and we have to set it equal to 0 because we want to find what is the minimum energy at that transition when that free energy gets obtains its minimum. So now this thing is A naught T minus Tc 2m plus 4bm3. So what we can do is we take the m common. It is A naught T minus Tc times 2 plus 4bm square is equal to 0. Now say that it is a ferromagnet. For a ferromagnet, that m cannot be 0. It has some magnetization left. So what we have is this quantity has to be 0. Okay, so 2A naught T minus Tc plus 4bm square needs to be 0. So this gives me m square is equal to minus 2 a naught by 4 b t minus tc. Now you see the slope of, say, m square versus t is a straight line with a negative slope, and uh, so that is what you see at, and when t is equal to tc, m square is equal to 0. When t is equal to tc, m square equal to 0, m square versus t is a straight line, and it has a negative slope. So this option matches with your answer. So this is your solution. So at close to transition, what you have to do is you have to just apply this formula. The free energy is minimized with respect to the magnetization. I hope this point is clear. So now what we need to do, let us go to the next question, the second question. The cyclotron frequency of a harmonic oscillator is given, and if the cyclotron frequency is given, then we know this angular frequency as well by this formula, and the magnetic length of an electron, this is what we need to find. So magnetic length of, like, for an electron in magnetic field, it is given by L of V is equal to h bar c over E B for an electron in some magnetic field. Okay. Okay. So it is given by this formula. So there has to be some magnetic field. Okay. In that context only, uh, uh, this is useful. Now, what it is given, so how do we find this B, and all three are given. So this B is determined, so this B determines something called the cyclotron frequency, or omega C. Omega C is equal to 2 pi fc. This fc is given. Okay. So, and this is, so the cyclotron frequency is given by E B over mc, where this m is mass of the electron, this c is the speed of light, and b is the magnetic field, and a is the electronic charge. Now you see here, omega c is equal to E B over mc. Okay. So EB over C is equal to m times omega c. Okay. Now this is what we will substitute in this expression. So what we will get is h bar, and EB over mc is EB over c is m times omega c. Okay, and h bar m we know, and this is omega c is 2 pi fc. This is what we have to find. So we know that h bar is equal to 1.055 into 10 to the power minus 27 second, is equal to 9.1 into 10 to the power minus 28 grams, and fc is equal to 2 into 10 to the power 11 hertz. Okay, or this you can convert to SI units and then again convert back to centimeter. Okay, and from here, so you just have to put everything, and what you will get is 0.961 into 10 to the power minus 6 centimeter. Okay, you just have to put all this value in here. That's all. Okay, so now let us go to the next question. I hope this question is clear. So now the question has given the potassium metal has electron concentration of 1.4 into 10 to the power 28 meter cube. So the concentration of electron has been given into 10 to the power 28 per meter cube, and the corresponding density of states at the Fermi level. So it is the density of states at Fermi level, it is given. So this means it is the number of states per unit energy per unit volume. So it is 6.2 into 10 to the power 46 joule per energy per volume. So it is per joule per meter cube. Okay. The Pauli, and it has asked what the Pauli paramagnetic susceptibility of potassium is given. So polyparamagnetism, it says that it is just according to the polyparamagnetism, the way we derive it is just for a brief outline. So it occurs in case of metal, and in metal not all the electrons participate in this paramagnetism. So initially, let's say that we have some density, we have usually the density of states like this, right? So this is density of states with respect to the energy. So if we take here the density of spin half particles and the spin half electrons, and here density of spin down electrons, and the magnetic field is in the direction of, so earlier it would be in this direction, it would be the density of states would be like this. So earlier the density of states would be something like this, but now as you switch on the magnetic field, what happens is and the magnetic field is along the up spin direction. So up means which is spin aligned along the aligned along the magnetic field. So here the density of states, it will just shift. So earlier, let's say this was your Fermi energy, so it will now shift to here, and this will shift up. Okay, and the extra electrons here, they will try to jump back here. So you will have more spin half particles. Okay, you will have more spin half particles, plus half particles than minus half particles. So due to this, so you can obtain, so by counting the number of what is the increment of this number of electrons with plus half spin, you will get this formula, and then you have to, so you will get the magnetization, and from magnetization you will get chi is equal to m over h. So this is how you do if you go through the lecture as well, or in some books also you can find. So what you get is the formula as mu naught mu b square and d of EF. Okay, now what you have is, you see, the number of electrons is you have Ne. So the number of electrons is already given, 1.4 into 10 to the power 28. The density of states is already given, this value you can directly put it over here. What is mu b? Mu b is the magnetic moment of the electron, that is also given, and permeability of the free space, it is also given. So here you have to put in 4 pi into 10 to the power minus 7. For mu b, what you have to put is 9.3 into 10 to the power minus 24 joule per Tesla, and d of F you have. So when you put everything, what you will get is 6.735 into 10 to the power minus 6. Okay, so this is what you have to do. You have to basically use this formula. Everything has been given in the question. Now let us go to the next question. The Larmor frequency is the frequency of precision of. So the definition of Larmor frequency is that it is the precision of so Larmor frequency, it is the precision of angular momentum. So it is the total angular momentum. Okay, around the external field. So what is, suppose if you have this as external field B, then the spin won't align completely in this direction. So there will be some tilt of the spin. Okay, spin means this total angular momentum, the spin plus orbital angular momentum bar. Okay, they will have some net angular momentum along this direction. So this will start spinning around this. Try to spin around this, and this spinning is called Larmor precision. Okay, and the frequency at which this spinning of this orbital angular momentum takes place is called Larmor frequency. So basically you have to so this is the correct answer. It is the total angular momentum J about the magnetic field V. Now let us go to the next question. Which of the following is true? Okay. Which of the following is true for an electronic cell designated by L, S and J? Here L, S and J are the total orbital, spin and angular momentum respectively. So one way to look at it is, so you can directly first method, you can do a brute force calculation and check that if the number of states here is equal to the number of states here or not. And there is another very like if you have followed what is Hund's rule, then you can easily determine which of this is true. So what we have is so let us go to understand how we can do this thing. So we have to basically calculate this quantity, sum over J is equal to, so J can take values from L minus S to L plus S, and we have to calculate 2J plus 1. What is this value? So how we can do that? So J, it starts from L minus S, L minus S plus 1, L minus S plus 2, so on. So it will go till L plus S, right? This L plus S is nothing but L minus S plus 2s. So now it will be L minus L plus 2s. So these are the values j will take. Okay. So when we go over this summation, so what we need to do is now, you see how many terms are there, you count these terms. This is the first term, this is the second term, okay, this is the third term, and so on. This will be to you note here here is 0, so it is the first term, 1 second term, 2 third term, so it is 2s. So this is 2s plus 1th term. Okay, so if we try to sum this over, so let us do this summation. So it is 2 times sum over j equal to L minus s to L plus s times j plus sum over j equal to L minus s to L plus s into 1. So this is what we have to do. So it is just so we have to sum over this j from L minus s to L plus s plus, you see here it is just the addition of 1, just this addition of 1 how many times. So 1 is added 2s plus 1 times, so it is just 2s plus 1, this particular term. Now all we have to do is we have to calculate this term. What is this? Now we need to calculate sum over j equal to L minus s to L plus s in j. Okay, so let us do that on the next page. Sum over j equal to L minus s to L plus s. So it is L minus s plus L minus s plus 1 plus L minus s plus 2, so on L minus s plus 2s. Okay, so this is what we have to calculate. So now say this, we just number it. Okay, this is the first term, second term, third term, and so on. This is 2s plus 1th term. So now see this L, it is just L plus L plus L how many times? 2s plus 1 times. So it is 2s plus 1 times L. Okay. Similarly this s is also getting repeated, minus s, 2s plus 1 times this s is getting repeated, plus what we have now is 1 plus 2 plus 3 plus so on. So it is 1 plus 2 plus 3 plus so on, 2s plus 1 times, up to this we have. Okay, so we know that sum over n equal to 1 to n, let's say this thing is nothing but 1 plus 2 plus 1 to n. So this gives this is given by n into n plus 1 by 2. This is the formula of that. Okay, so here similarly what it will be? It will be 2s plus 1 L minus s 2s plus 1 plus so here n is equivalent to this 2s plus 1 2s plus 2 by 2. Okay, so what we have is 2s plus 1, and this is so 2s plus 1 we can take common here, here, here. So it is L minus S and plus S plus 1. Okay, so this is nothing but 2s plus 1 into L plus 1. This quantity we have to add with the here in the previous slide. So here what we got is sum over this j is 2s plus 1 into L plus 1. So this is 2s plus 1 into L plus 1. Okay, so in next page. So we have calculated. So now we just have to plug this into here. And now you just have to plug this here. So what you get is finally sum over L minus S to L plus S to j plus 1. This is given by 2 times. So we will replace this sum by this quantity 2s plus 1 L plus 1 and plus 2s plus 1. Okay, so what we have now, so on simplifying this one, what we get is 2s plus 1 to L plus. Here I have to take here we have to take care of this problem. So it is one, it is starting from 0 actually. So here there is this sum would be, it is so, so it is actually the sum over 1 plus 2 up to 2s, not 2s plus 1. So this sum would be a bit different. So this would be 2s 2s plus 1 by 2. So here we have to do, it is 1 plus 2 plus so on up to 2s. So what we have is 2s plus 1 l minus s 2s plus 1 plus, so here up to 2s we have to take. So it is 2s 2s plus 1 by 2 by this formula. So what we have to do now, we can take the 2s plus 1 common. So it is l minus s and plus s. So what we have is l times 2s plus 1. So this we have to put it over here. So here what we have is, it is l times 2s plus 1. So by the calculation in the next page, and when we put this over here, so what we get is, two times 2s plus 1 and this l plus 2s plus 1. So this will give me 2 times 2s plus 1 and sorry, 2s plus 1 times 2l plus 1. So this is your answer, and so I hope this is clear. So since we have proved that this is answer, the rest of all are not the correct answers. So you have to keep in mind how to evaluate these particular terms. So uh, so this is how you have to go for this calculation. Now let us go to the next question. Here you see, as shown in the figure, the inverse magnetic susceptibility, this is 1 over chi, it is plotted as a function of temperature for 3 different materials in paramagnetic states. Okay, and the Curie temperature for paramagnetic state Tc is given, Néel temperature for antiparamagnetic state is given, and choose what is the correct from the following. So see, we have uh, this for the magnetic susceptibility for different material, like for different magnetic states, the susceptibility is given as the susceptibility chi is given as C over T for so this is, we know, for paramagnetic material, paramagnetic material. So if you do 1 over chi, then this would be T over C. you see this 1 over chi is directly proportional to temperature, and it so when T is 0, 1 over chi goes to 0. So this should correspond to paramagnetic state. Okay. Okay, now for a ferromagnet, the susceptibility is given by C T minus Tc, where Tc is some critical temperature. Okay, now if you do this, you take 1 over chi of this. So this we know from this the expression for ferromagnetic susceptibility. So this is T over C minus Tc over C. But this C are like C is a constant. You see here, so 1 over chi, if you plot on y-axis and this on x-axis, then you have an intercept which is negative, which will intersect the y-axis on negative. Okay, so and it is, you see, this particular curve is intersecting in this negative axis. Okay, so the intercept is basically negative, and that is happening for a ferromagnet. So this should correspond to a ferromagnetic state. Then for an antiferromagnetic state, what we have is the susceptibility for antiferromagnetic state. It is given by chi is equal to C over T plus, here there is something called Néel temperature. Okay, now if you just now simply inverse it, it is T over C plus Tn over C. Now you see here it is a positive intercept. So a positive intercept is here. So this should correspond to antiferromagnetic state. Okay, so now the option which matches this is your solution. So the material 1 has to be antiferromagnetic. So material 1 is antiferromagnetic, 2 is paramagnetic, and 3 is ferromagnetic. So yeah, so this is your solution. Now let us go to the next question. So electric field and magnetic field are given, and we have to find the parity of E dot B. So we have to see if it is its parity and time reversal, what if it is even or odd. So we first look at the Lorentz force. So force is nothing but, so it is the Lorentz force. So E plus B cross B. Okay, and from Newton's law we know that d2x over dt square. Okay, now to see if some quantity is odd or even under parity, to check parity, what we do is we take x to minus x, y to minus y, and z to minus z, and we see under this transformation is our relevant quantity changing or not. Okay, now see, force is always odd under parity. Force is force is odd under parity. So what this means is, if you, so in this equation, if you take this coordinate, this r to minus r, because you have to go under this transformation, r will go to minus r. Okay, and when r will go to minus r, the second derivative of it will also go to its negative. So therefore you see there are two terms here. If you look at the first, so this is a constant. this is a constant E, or the electronic charge is a constant, and the physical quantity is electric field. So if this is odd under parity, then the electric field also has to be odd under parity. So E is odd under parity. Okay. Now, okay, let us consider V. V is what? dr by dt. So velocity is, if you under this particular transformation, so under when r will go to minus r, v will also go to minus v. Okay, so this is, so velocity is also odd under parity. Okay, now let us look what will happen with b. So if the velocity, this is odd under parity, this thing is odd under parity, so the magnetic field now has to be even under parity, so that the odd and even, they will give an overall odd parity. So this magnetic field B is even under parity. So therefore their dot product, so product of odd and even is always odd under parity. So E dot B, so odd and even, so under parity it will be odd. So we'll have this odd under parity or odd under parity. Now let us look at the time reversal. So to understand the time reversal, what we have to do is we have to think of so let us imagine that there is an electron here, and the electric field is like this. So electric field is like this. So we take a video of this particular. Let us imagine that we are taking a video of this electron, and then we play the video in backward mode. But the electric field here, will still see that there will be no change in the direction of the electric field. So the electric field is, so since there would be no change in the direction of electric field, so electric field is even under time reversal. Now consider what about the magnetic field? So the magnetic field can be generated if the electron is, let's say, it is rotating in a circle. Okay, and the magnetic field generated due to it will be like this, somewhat like this. Now what you do? Now you take the video of this electron rotating, it is revolving around some axis. Magnetic field is like this. Now now you take the video of that electron revolving and play it backward. So now the electron, so in that video which is playing backward, the electron will be revolving in an opposite direction. So hence the magnetic field will become opposite. So the magnetic field will become opposite because the sense of rotation has become opposite. So therefore magnetic field is odd under time reversal. So now, and the product of even and odd quantity, it will give me odd under time reversal. So here what we need is this odd under time reversal. So this is your option, correct option. I hope this concept is clear. Now let us go to the next question. So what is the value of commutator A dot P, or this A P? A is the vector potential, okay, and P is the momentum, and what A is in, we are given this condition. This condition is also called Coulomb gauge. So let us try to do this. So, and what this commutator means? Commutator means A dot P minus P dot A. And remember that this A and P are operators. So P is the operator which is given by minus I h cross gradient. Okay. And we have to, since this is an operator, and we have to check how this quantity operate on some function R. Okay, this is some scalar function, and on this we have to operate these operators, and we have to see how it behaves. So let us do A dot P of psi of R. On
Hello.
doing this,
In last question, why we have done from the that force equation we find the E and B, uh, that we have find the parity of that E and B, right?
yeah,
Sir. So here can we not find with another way the parity of the E and B?
parity of E and B. Another way means, which way you want to know?
Means like here we are finding with the help of force from the right.
Yeah,
Uh,
so there may be other methods as well. So, but what I was trying to say is, see, what is parity? To find the parity, you have to. Uh, so what do you mean by parity? Parity
yes.
means. Uh-huh.
Continuous.
Uh, you want to say something?
No, no, sir. Continuously.
Yeah. So what parity means is, just a second. Any physical quantity. So for any physical quantity, let's say uh, any quantity, let's say Q. Okay. So we have to see how to find it is odd or even under parity. Okay. So parity, what it means is that, so parity, it is a type of symmetry. Okay. And what do you mean by symmetry? So we do some particular operation, and we examine the system, examine the operators, or like, and uh, so we do some operation here for the parity. The operation is what? See, in general, to study any symmetry, okay, to study any symmetry, we do some operation, and we study how that system behaves in case of this particular operation, and then we say it is what kind of, we conclude about the symmetry. Okay. For example, uh, imagine that there is a triangle, and the operation is rotation by 30 degree. Sorry, rotation by 120 degree. Okay. Rotation by 120 degree will give you again the same triangle, right? So rotation by 120 degree is a symmetry operation. uh, so similarly here, our to check the parity, the relevant operation is, you take the coordinates to negative of the coordinates. Okay. And you see if the relevant physical quantity are changing or not. Here the, for example, here you are seeing triangle. We are actually looking at the electric and magnetic fields. Okay. So under this transformation, you want to say something? So understand this concept?
Yes, sir. Actually, it's only shows na sign of the negative and positive, right?
Sign of negative and positive.
Like in odd it will show negative and
Yeah, yeah.
positive.
So those
Yes.
are the two symmetry states, right? It can be either odd or
Uh,
even.
yes.
So that I will tell you. So why we are using particularly the force equation? So see, we have to see how the coordinates, this coordinate system, this axis actually changing this coordinate system. It has to come into the picture, right? We have to see this when this r is changing, and there in the expression of force we have this d2r by dt square. Here we can check that how changing of this r plays a role. So parity is nothing but changing of this r to minus r, right? So that is why we need an expression in which that r should be there. That is why we looked at the force equation. You got it?
Yes. Actually, the R is the dependent thing, or else it shows any other function that can show negative in after parity. Negative, yeah. R two, it R is changing in R minus.
Yeah.
So, so it is it necessary to take only R means we can go with the any other function. I don't want to be dependent with the any function. It what actually says with the E and B.
You don't want to be what?
So actually, we are taking only R, right? So and there we are taking the equation. Is it for calculating the parity? Do we need only for R means like any function R?
Yeah, you need to examine how it depends on the coordinate system, right? Because at
Yes.
the end, what you have to check is you have to check how the relevant quantity will change when you change the when you change from r to minus r. So that is why you need a function with r. Got it?
Okay. Yes. Yes. It's from basic we just find out the is it it will show parity or not.
Yeah. So uh, this is the basic route how you go about.
Okay, so actually all functions shows the parity means or it is the only some function shows parity.
See, you can examine if parity is existing or not for any quantity. Like for example, you can check if angular momentum shows parity or not. Or so angular momentum is what? R cross P. P means m times dv by dt. dr by dt. So this is your angular momentum, right?
Yes.
So now under parity, what will happen to this? This r will go to minus r cross m d by dt of minus r. Okay, so this will again, this minus will cancel minus, and this L will remain unchanged. So angular momentum is even under parity. You got it?
Okay. Yes.
Or like you can think of any other quantity. For example, what other quantity you can think of? Some other complicated function, anything, uh, like anything you have to do this r to minus r you have to change and check for parity.
Okay, sir. Okay, means it depend on the power of R also. Here it was two R, so it got cancelled because minus minus positive, right?
Yeah, true.
So it depend on the power of the R also, right? So,
So it
okay.
depends on like you you just if someone says you how you want to check the parity. So you what you have to do, you just put so there would be an expression which will have r. You take r to minus r,
Oh,
and then you see if the expression is changing or not.
yes, yes. Got it.
Yeah. So that is how you have to check.
Okay, thank you, sir.
Yeah. Okay, so we are discussing this question. So the we have to find this commutator, right? So A and so we'll do that in the next page. So A is an operator and P is also an operator, and we have to check how this operates on a function of R. Okay, and what is P? P is minus I h cross this gradient operator. So let us now do this. Uh, so A dot P of psi of R minus P dot A of psi of R. This is what we need to find. So what is this quantity? So we'll now replace P, put P is equal to minus I h cross this. So A, this is minus I h cross gradient psi of R. Okay, now this is gradient of psi of R minus, what is this thing? Minus I h cross this. First we'll have to operate A on this. So that may, so and A is just A operating on this means A is multiplying with this function A into psi of R. So this is nothing but minus I h cross A dot product with gradient of psi, and this is plus I h cross. So and this will be two terms. One is divergence of A times psi of R plus I h cross, you have to leave A, and so it is just chain rule. Okay, divergence of psi, gradient of psi of R. Now you see this quantity is same as this quantity, so this cancels this, and all we are left with is I h cross divergence of A times psi of R. But if you look at the question, we are given that we have to work in the Coulomb gauge. Coulomb gauge is divergence of A is equal to 0. So this is 0. So we get 0. So this means this operator A dot P is nothing but 0 operator. So your correct answer is this one, the last option. Now let us go to the last question. According to Hund's rule, which one of the following is false? So Hund's rule, so just to remind you, Hund's rule is like with Hund's rule, what you can do is you can find what is the, like for example, there is some filling of electrons of an atom. Let's say D cell. Okay, so D cell will have this ml values minus 2, minus 1, 0, 1, 2, and Hund's rule tells you that the spin has to be first aligned so that the spin is maximized, and then S is equal to whatever the spin that is there, so 1 by 2 times what is the number of the free spins. L is equal to what is the sum over this ml values, the sum over sum over ml values. Okay, and J is like L minus S if it is less than half filled, and L plus S if it is more than half filled. So basically this rule, this takes into account how this, so S is what? S comes from the spin and L comes from the orbital angular momentum. This is the spin angular momentum, this is orbital angular momentum. So and J is what? J takes into account how this how the spin and angular momentum they behave, they interact with each other. So if so the first statement, the rule does not consider the energy shifts due to the spin orbit coupling. So this is wrong or false because it takes into account. So and particularly you will have some this L dot S type of terms. This signifies the spin orbit coupling. So it takes into account into that. So now the second option is due to the Pauli exclusion principle, two electrons cannot share the same set of quantum numbers within the same system. This is true, and like true of all the fermions, and electron is a fermion, and that is why it should obey Pauli exclusion principle. This rule deals with reducing the repulsion between electrons. Yeah, that is also true, because here the way we fill is we have to first fill such that it goes to electron goes to different orbital. So this is nothing but just to reduce the repulsion of the electrons. J is L plus S for more than half filled and L minus S for less than half filled cells, where J, L and S are the total. So this thing is true. So this is just one of the Hund's rule. So that is all about the assignment of this year. Okay, so now there is one more question here, the 10th question. What are the spin, orbital and total angular momentum values for this is Z equal to 26. So Z equal to 26, and this is a transition metal element, and we'll look at the electronic configuration. So there are 26 means there are 6 electrons in the outer cell. Okay, so this is like argon, and this is 3d6, argon is 18, and 4s2 3d6. So this is a totally filled cell. This is electronic configuration of the iron. Okay, so D means L is equal to 2. Yeah, sorry, this L. Okay, and since L is equal to 2, so this is D subset D. So the ML values will have -2, -1, 0, 1, 2. And how do you should apply Hund's rule? So number of electron is 6, and if you want to apply Hund's rule to fill the electrons, how do we fill? 1, 2, 3, 4, 5, 6. Okay. Now S will be what? S will be how many spins? So up, down, this spin cancels. So plus of plus of plus of plus. So 4 times 1 by 2, it is 4 into 1 by 2, it is just 2. S is equal to 2. Now L will be what? L will be, what is the total? So L is nothing but the magnitude of L, magnitude of ML. Okay, so this -1 cancels -1, 0, and 2 cancels -2, it is just 2. So L will be also 2. If you sum over all this, so it is -1 plus 0 plus 1 plus 2 -2 -2, and you have to take the magnitude of that. So L is equal to 2, and you see this is more than half filled, more than half filled. So what we will have is J is equal to L plus S and its magnitude. So L plus S is 2 plus 2, it is 4. So J will be equal to 4. So it is 2, 2, 4. So this is your correct option. I hope this is clear. Now let us look at some of the previous year questions. So which of the following nuclei does not have a zero spin? Okay, so what we have to look at is, let us look at the electronic configuration. So oxygen, so this 17 is what? 17 is the number of nucleons. So for example, when I say 17O8, it still has 8 electrons. 8 electrons. And 8 electrons means what? So for oxygen it will be 1s2, 2s2, 2p4. Okay, the p subcell can have a total of 6 electrons, but it can have a total 6 electrons. Can have total of 6 electrons, but it has 4. So this 2p cell is this implies that 2p cell is not filled. Okay, so this will have uh, some non-zero spin. It will have some spin because this cell is not filled. Okay, because like if you see, uh, there will be three p cells, right? Px, py, and pz, or like ml equal to -1 0 1, and they have four electrons, 1 2 3 4. So you see, there are two free cells, and like you can think like 1 by 2 plus 1 by 2 equal to 1. So s equal to 1 by 2. So this does not have a zero spin. Like, but if you see the others, for example, magnesium is what? Magnesium will have 12 electrons. 12 electrons. So it is 1s2, 2s2, 2p6, and 3s2. So s can have a total 2 electrons. It has C. It has total filled electrons. So what about calcium? Calcium has 20 electrons. So 40 calcium 20. So it is 1s2. So basically it is argon 4s2. Okay, argon has a filled cell 4s2. Okay, similarly, strontium also has strontium. Uh, if you look at the it will have 38 electrons, so which amounts to uh, it also amounts to a filled cell. Okay, so it is argon and 4s2, 3d10, and 38, right? So argon will have 18, and so if you look into literature or the periodic table, you will find out that it will have a filled subset. So uh, strontium. So for strontium, you can just check. It will have a filled subset. For example, the last cell, I think maybe 3. Just check. So, so it is 2, 8, 18, 8 and 2. So this amounts to 38, I guess. 2. So it is 1s2. This is the second cell, 2s2, 2p6, and this is the 3. So this is 3s2, 3p6, 3p10, and then 4s2 and 4p6 and 4s4p and 5s2. So this is the electronic configuration of strontium, which you see all the cells are filled. So that is why it is also, it doesn't have a zero spin. So it has a zero spin. So now let us go to the next question. So here the interaction energy of the magnetic moment in a field is given by this. The interaction energy expression is given, and mu z is the component of the magnetic moment in a direction of magnetic field. Here we write mu z is s mu for electrons, where s is equal to plus minus 1. Okay. So we have to calculate the partition function for n non-interacting spins Zn. So from statistical mechanics, what you can simply do is that uh, uh, so there are two ways to solve this problem. So you have to find the total number of energy configurations and get the partition function Zn is equal to sum over all the energy configurations sigma e to the power minus beta e. Uh, so e sigma is the for each different configuration. Each different configuration means when I is equal to si s1 equal to 1 and all others are 0, and s2 equal to 1 all others are 0. So similarly you will have different configuration. So you can prove that by, if you just go through this, you can prove that it will be nothing but the partition function for one particle times n. So this can be proven from statistics, can be proven. Okay. Now all we have to do is to look for what is the partition function for the one particle system. So the partition function for a single particle will be given by so it is now easy. For a single particle there can be e to the power, so there the energy can take only two values. So e can take one value, uh, so mu z h and minus mu z h. Okay, and it will be mu z h and minus mu z h. So e to the power beta mu z h plus e to the power minus beta mu z h. So these are the two energies it can take, and so basically it is 2 cos h beta mu h. Okay, so this is what you have z1, and for n non-interacting particles it is z1 to the power n. So it is 2 cos hyperbolic beta mu h to the power n. Okay, and now once you have this partition function, the free energy is nothing but minus kBT ln z. Okay, so it is just minus kBT ln, and so it is 2 cos h beta mu h this whole to the power n. So and log of something to the power n, it is just minus n kBT ln 2 cos beta mu h. So another thing you notice is that for a single particle it is just n kBT 2 cos hyperbolic n. Okay, this was for single particle up to this much. But since they are non-interacting spins, so n non-interacting spins are there, the free energy just gets multiplied with the number of particles. So intuitively this is also like clear. So what we have is the correct option would be I think this one. Now let us go to the next question. By making use of the answer of question 2, what is the correct expressions for magnetization? Okay, so the magnetization M is given by minus tau of free energy, the derivative of free energy with respect to H. Okay, and we have the expression of this dou by tau H of What is f? F is nothing but kbt minus kbt ln 2 cos hyperbolic beta mu h. This is what we have. So all we have to do is take the derivative with respect to h. So this minus cancels minus, and it is kbt, and when you take this derivative, it is 2 cos beta mu h, it is 2 sin beta mu h, and it is beta times mu. So it will be, and f also has, f has this n kbt. Okay, that is this n, and so what we have is n mu tan hyperbolic, so sin hyperbolic by tan hyperbolic beta mu h. So this is your expression for the magnetization. So it is n mu tan hyperbolic beta mu h. So either this or this. So now what we want to find is the susceptibility. The susceptibility is given by the derivative of m with respect to h. So magnetization with respect to the field. So it is just dou by dou h of, we have to use this expression just derived. So it is n mu tan hyperbolic of beta mu h. So it is n mu sec h square beta. It is just the derivative of this tan hyperbolic, and it is beta times mu. So beta n mu square, so beta n mu square sec hyperbolic. So this is your correct answer. So this is what you have to do. Okay, now we are asked what is the pair of ions which have J equal to 0 but L and S not equal to 0. Okay, so how do we find this thing is, let us look at this. Let us look at the two so these elements. What is manganese 3 plus? So manganese 3 plus, it has electronic configuration this. So it has Z equal to 25. Okay, and chromium has Z equal to 24. Okay, and if you look at the electronic configuration, like let's say it is argon Z equal to and 4s2 3d5. So this would be the so this would be the ideal configuration, but we have this 3 plus here. So what we have is, so we have to remove the 3 electrons from here. So how do we remove the 3 electrons? So from outer cell this 2 will go, and this is Mn, and Mn3 plus Mn3 plus, we have to remove 3 electrons. So from outer cell we have to remove 2 electrons, and from the inner cell 1 electron will remove. So it is 3d4. So this is Mn3 plus. Okay, so it has 3d4 configuration, and this is chromium. So chromium is, it has electronic configuration like this, 4s2 3d4, and chromium 2 plus we have to now remove 3d5. Yeah, 4s2 3d4. So we have to remove the 2 electrons. So it is argon, so 4s0 3d4. Okay, so these both are this uh, both of these have d equal to 4 fillings. Okay, so if we try to do d for d means what? So we have to ml values, ml minus 2 minus 1 0 1 2. Now we'll apply the Hund's rule. Hund's rule. If we apply Hund's rule and we have to do d4, right? So 1 2 3 4. Okay, so as we have what? S is equal to 4 times half, which is 2. L is equal to, so sum over all this, minus 2 minus 1 plus 0 plus 1. So and we have to take the magnitude of that. So S equal to 0. So we need this J equal to 0, right? So for J equal to 0, what we need is L minus S something, and Ls not equal to 0. So L minus S needs to be 0, which means L has to be equal to S, and it has to be less than half filled. Less than half filled. Okay, so here it is, since it is less than half filled, like D4, we can use J is equal to L minus S, and here we have is exactly 2. So this is the correct option. Now you can check for the others if they are true or not. So you can apply directly the Hund's rule and you can check. Uh, so and you can look into the periodic table to see their electronic configurations, and you can solve for the you can check for the other elements as well. Now let us go to the next question. I hope you know how to solve this kind of problem. Now it has given, so which of the following has or have S equal to J. So we need S is equal to J, and the options given are M and iron 3 plus and cobalt. Okay, so let us, and so what we need is, all we have to find is that uh, L has to be 0 because S is equal to J, right? So J is equal to L minus S if it is less than half filled, and L plus S if more than half filled, right? So if L equal to 0, then only we will have J equal to S. So L equal to 0 can be when, suppose it is mine. So we'll look at the ML values, and you see this is a D block element. So D cell we have to fill 0 1 and 2. Okay, and L equal to 0 if we have some this kind of situation. Okay, and so basically all we need is 5 electrons, or this kind of configuration. Either it is totally half filled or completely filled. So we need 5 electrons in the cell. So we can directly see that this Mn Z equal to 25. Mn has this configuration. Just now we saw 4s2 3d5. So Mn will have L equal to 0, but S equal to non-zero. So S equal to basically 5 by 2. So J also will have 5 by 2. So Mn is one of the options. So either this or this. We have to check for Fe3 plus. So Fe has electronic configuration this. Fe3 plus has Z equal to 26, and we have to Fe has Fe4s2 3d6, and Fe3 plus will have electronic. We have to remove 3 electrons from here. So argon 4s0, and we have removed 2 electrons, and 3d and 1 electron from here. 3d5. You see, Fe3 plus also has 5 electrons. So Fe3 plus also will show S equal to J. This also will show S is equal to J. So your correct answer is this one. Now let us go to the next question. Is there any question? You got it right? How it is solved? I hope it is clear.
So S and J we are getting from that electrons ups and downs.
Yeah, we are getting J from here. Electron up and down.
K answer S.
Huh?
And S and J both are getting from there. Actually, once can you repeat once? Yes.
This solution. Okay, just tell me.
Yes. This one only.
Yeah. So what it is asking is, see, uh, so it is asking, you first you look at the question. It is asking which of the following have S is equal to J, right?
Yes.
So we want to find S is equal to J. So we would look for those configuration, and we know that J is equal to either L minus S for half filled or L plus S, right?
Yes.
But since it is asking J equal to S, we need has to be 0. This is clear?
Yes. Yeah.
Now L can be, what is L? L is nothing but sum over all these ML values, right? Its magnitude.
Yes.
And this can be possible if we have, like, when we fill the electrons in such a way that all of this is filled, so that it is minus 2 minus 1 plus 0 plus 1 plus 2 for all these 5 electrons, so it will be 0. So we need exactly 5 electrons in the D cell. This is clear.
Actually, is the D cell is the outer cell of the ML?
We need 5. Yeah.
Sir, is the D cell the outer cell of the magnesium? Sorry, manganese.
Manganese. Yeah, so we write it like this, but no, the outer cell is actually the 4s cell is the outer cell, but we write it this way because during the filling it is 4s gets filled first. Like, there is something called Aufbau principle. According to that, 4s gets filled first.
Yes, yes. Okay. Okay, sir.
Okay, so we need 5 electrons in the D cell. You got it right?
Yes, sir. Got it because it is outer cell. Yeah.
Yeah. So now, for this you check what is the S. So L will be 0. S will be just 1, 2, 3, 4, 5. So it is 5 by 2. And J is nothing but L minus S or L plus S. So it is again 5 by 2. So that is how it is. Understood?
Yes, sir. I got that point. Only, but this thing is uh, ML. We have to get the zero, right? ML.
Mn.
L. Sorry, MN. You know. Okay. I know there is the value of L. We have to get zero. So that zero we will get from uh, ML
See,
is equal.
yeah, ML, you just have to sum over all ML. Okay. So how do you sum? So this sum over ML is what? This L equal to minus 2 here. Then L equal to minus 1 for this electron.
No, no,
Okay.
but how do we know that it will be only minus 2 from plus 2? It is going
See,
from.
it is in D cell, right? It is, see, this is D cell, right?
Yes, sir, D cell.
Yeah. So we know that D cell has the value of L. Like, for what is the value of S, P, D, F? For S, L equal to 0, T, L is equal to 1, D, L equal to 2, F, L equal to 3. You know this, right?
Okay, from yes,
Yeah.
I know.
And the ML value will be for S it is just 0, for P it is minus 1, 0, 1, for D it is minus 2, minus 1, 0, 1, 2. You understood this?
Yes, I got it.
Yeah, that is what it is. Okay.
Okay, thank you, sir.
Okay, we go to the next question now. So, cobalt forms an atomic vapor at 2000 K and some vapor pressure is given. You can consider this vapor to be an ideal gas. What is the paramagnetic contribution to the Curie susceptibility of this gas? Okay, so we have to find the paramagnetic contribution. Okay, so there is this for so we have to first find the Lande G factor. Okay, Lande G factor, and it is given by 3 over 2 plus s into s plus 1. So for cobalt we will find what is L, J and S, all this quantity, L plus 1 over 2 J, J plus 1. Okay, so after we find this L, J and S, the Curie susceptibility, it is just given by, so let us see what is this Curie susceptibility. Okay, uh, Curie susceptibility, the formula is just chi, the molar susceptibility, it is given by Na G mu B. So this is the formula that you have to kind of know. So J into J plus 1 over kVt. So basically you need to find what is this G. You want to find what is the value of this G, Lande G factor. Lande G factor. We have to find what is the total angular momentum, and mu b is the Bohr magneton, you know, and this is your Avogadro's number 6.022 into 10 to the power 23. And temperature, you know, this is Boltzmann temperature is given in the question, 2000 Kelvin, and Kb is the Boltzmann constant. Boltzmann constant. All you need to do is to find this G, and to find G and this J. These two you have to find. And to find this, you need to find what is, you have to apply Hund's rule. Apply Hund's rule. And apply Hund's rule, find J, L and S. And when you know this J, L and S, you can get G, and you have to put in this formula. So let us do that. So for example, for cobalt, it is Z equal to 27. So let us just do that. So cobalt Z equal to 27 means it is argon 4s2 and 3d7. Okay, now let us apply Hund's rule. So these are the ml values, minus 1, minus 2, minus 1, 0, 1, 2, and we have to fill 7 electrons, 1, 2, 3, 4, 5, 6, 7. So from here what will be S? S will be just, so this is plus of minus of cancels, plus of minus of cancels, so plus of plus of plus of, so it is 3 by 2. L is what? L is, you see, minus 2 plus 2 cancels, minus 1 plus 1 cancels, 0 is 0. So we just have minus 2 minus 1, it is minus 3, and we have to take the magnitude of that. And J, since it is more than half filled, so it will be just L plus S and its magnitude. So J will be equal to 3 plus 3 by 2, which is nothing but 9 by 2. It is basically 3 plus 3 by 2 and its magnitude. Okay, so now uh, so we got S, we got L, we got J. So we have to now put it in the expression for Lande G factor. So G equal to 3 by 2 plus S into S plus 1. So S is 3 by 2 into 5 by 2 minus L. L is 3 into 4 divided by 2 times J. J is 9 by 2 and 11 by 2. So it is just 3 by 2.
For Curie accessibility, we have the formula for x is equal to c by t also, right?
C by but this is there in terms of this J. So you have to use this particular formula.
Okay, this formula I didn't encounter with this. That's why I asked.
Yeah.
How do we find this formula?
So,
Okay,
see, this comes from that. So if you go through the derivation of free spin, but the spin need not be like spin half. Like so, there was one derivation where we used to do this thing. That Brillouin function was used. Like you need to go through some book.
okay, okay,
Okay.
okay.
So basically, you'll come across this.
Okay, actually, that formula Curie accessibility I got in the nuclear physics.
Okay.
Yeah, x is equal to c by t. So here, how is it working with the that I don't know. So that's why I asked you.
How is it working? I mean, you want to know the derivation of this.
No, yeah, I just
Uh,
you can tell me where you can find the.
where you can find. Maybe I will post some of the references to this. Okay, in during the while posting the video.
Hmm. Okay.
Uh, like I have to look right now where I will find this.
Okay, sir. Thank
I'll
you.
send some references for this.
Okay, fine.
Okay, so I think you just have, you can uh, so you can simplify this, and what you will get is, so on simplification you will simply get 4 over 3, and you can now put everything, and you will get the, so everything is now you have all the required quantities, and you'll get the solution to be this one. Okay. uh, Now let us go to the next question. So it is saying that a diamagnetic sample contains some ferromagnetic contamination, and there will be a temperature dependent contribution to the total magnetic susceptibility. Then the total susceptibility is given by, okay, so diamagnetic, so the total susceptibility is like this diamagnetic plus uh, the susceptibility of, so there is some contamination, right? This ferromagnetic contamination, ferromagnetic. So and so we know that, so there will be some diamagnetic, it is given by this there, and we know that this ferromagnetic susceptibility is given by this T minus Tc. Okay, so this is what we get for some uh, ferromagnetic material. So the total susceptibility is nothing but just the sum of this. So it is just straightforward this. And here, what are these all questions? So this is for, this particular term is for antiferromagnetic term. Okay, this is antiferro, and this is paramagnetic term, paramagnetic susceptibility. Okay, so since the question is asking of ferromagnetic contamination, this will be your correct answer. Now let us go to the next question. The diamagnetic susceptibility. So this is also a directly formula based question. here if you look at the uh, if you look at the uh, formula for diamagnetic susceptibility or the molar dielectric susceptibility, it is just minus z, so e square over 6m. So this you can find during the lecture or in any standard textbook also you can find. Na is the Avogadro number, and you have to take the average of this r square. Okay, r is the radius of the electron. Okay, and r square, it is just saying that you have to take uh, yeah, you have to take n square. Okay, a square, r square is approximately is a naught square, and a naught, its value is given the Bohr radius. Okay, uh, EMC, you know, so this is Avogadro number 6.022 into 10 to the power 23. R square is equal to A naught square. This also you know, A naught is equal to 0.529 into 10 to the power minus 8 centimeter. And M, you know, it is 9.1 into 10 to the power minus 31 kg. C, you know, speed of the light, C is equal to 3 into 10 to the power 8 meter per second. E is the electronic charge, so it is 1.6 into 10 to the power minus 19 coulomb. And Z is what? Z is the number of electrons of xenon. Number of electrons of xenon. So Z is equal to, so xenon, if you see the periodic table, it comes about 54. Okay, and if you put everything, so you will get this value. You put everything, and the value you get is minus 42.66 into 10 to the power minus 6 centimeter square per mole. It is just uh, formula based question. Now let us go to the next question. Which one of the following material susceptibility does not depend on temperature? Okay. Uh, you see, Pauli paramagnetism, just now we saw chi Pauli, it was something like mu naught mu p square and times the density of states at the Fermi level. So here if you see, this is independent of the temperature. Independent of temperature. Okay, but if the question is asking only the paramagnetic term, okay, so this if someone says only paramagnetic, it will have for example Curie paramagnetism we saw, right? It has some kind of this inverse temperature dependence. The ferromagnet has dependence of T minus Tc, and so this is the chi, okay, chi par, some other paramagnetic term, the Curie paramagnetism. And antiferromagnetism term also has a temperature dependence, and it is so it also has temperature dependence in the chi antiferro. Okay, so basically all of this is temperature dependence except polyparamagnetism. So this is your correct option. It doesn't depend on temperature. Now let us go to the next question, and here you see what it has given. So it has the molar okay, here the formula is already given. The ground state 1s of the hydrogen atom is also given, where A is the Bohr radius. Calculate the diamagnetic molar susceptibility and chi molar for this atom using the Langevin formula. See, so basically what we have to do, everything is there, minus z e square n a over 6 mc square r square. Okay, everything is there uh, because z for hydrogen atom is 1, for h atom z is equal to 1, e you know, m you know, c you know, na is the Avogadro's number. We basically have to find r square. Okay, so let us just r square. So what is this r square? Expectation of r square it is that psi star of r, okay, r square psi r, okay, integral d cube r for all space. This is what we need to find, right? And since there is a radial symmetry, we can take advantage of that, and what we will get is uh, uh, so this psi of r, this will give me root under pi a cube e to the power minus r by a and r square, and again pi a cube e to the power minus r by a integral, and this is d cube r, we can write it as 4 pi r square dr from 0 to infinity. So this is the expression we need to calculate, and so let us do that. So all we need is r square is equal to 0 to infinity 1 over pi a cube a to the power minus r by a r square 1 over pi a cube a to the power minus r by a and 4 pi r square dr. This is what we need to find, and on simplifying 1 over pi a cube and 4 pi and a to the power minus 2r by a and r to the power 4 dr and r equal to 0 to infinity. So this pi cancels pi, so what we have is 4 over a cube, so 0 to infinity e to the power minus 2r by a. So and we have this r to the power 4 into dr, so what we can do, 2 by a to the power 5 or 4 dr, and here we can do a by 2 to the power 5. Okay, so what we have is 4 and 2 to the power 5 a to the power 2 and 0 to infinity a to the power minus 2r by a and 2r by a to the power 4 and d of 2r by a. So it is a square over 8 and what we have is, so we substitute x is equal to 2r by a, so 0 to infinity e to the power minus x and this will be x to the power 4 dx. So this uh, this function is the gamma function, and it is nothing but 4 factorial, a square by 8 into 4 factorial. Okay, so it is gamma function. So gamma n is given by 0 to infinity e to the power minus t t to the power n minus 1 dt. Okay, and gamma n equal to n minus 1 factorial. I have just used that one. So it is a square by 8 into 4 into 3 into 2, so it is 3a square. So we got r square equal to 3a square. Now we simply have to put everything in this formula. So we got that this r square is nothing but 3a square. We got r square is equal to 3a square. A is nothing but your bore radius. Okay, and bore radius is there in your previous value. So you just put this, so minus z is square and a and 3a square over 6 and c square. Okay, and you put everything and you will get your solution as this. So this will be your solution. So when you put everything, okay. So this is how you need to solve. I hope this calculation is clear. Uh, so use this expression for susceptibility. Okay, so I'll just write here chi is equal to chi is equal to minus z is square and a 3a square divided by 6 and c square. So this is how you find your solution. Uh, so that's all for today. I hope you understood some of the techniques how to solve the question and answer. If you have any question or doubt, you can ask me.
Sir, I have one doubt. Can I ask?
Yeah.
Okay, sir. Actually, exam we can register yet for the 70 till 17 March, right?
Okay.
For
I
the,
am not sure about those logistics. Uh, like about the dates and all when you can register and all that I'm not so sure.
okay, okay, sir. No, okay, no problem. I want to ask like that. If I missed two or three assignment, maybe I have to see it. Actually, I submitted only one or two. So, can I give the exam because to get certificate?
Uh, that I don't know. I think there is some minimum mark you have to score,
Mm.
and then you will get the certificate.
Okay, okay, fine. So
Yeah.
I have
So
to.
yeah, maybe you can write a mail to maybe some to coordinator in your college,
Fine.
and they can help you. But I would recommend like you if you want the certificate, you go through all the assignments, and you can follow the previously recorded video. You can like go through this and
Okay, sir. So next time it will be now there. It is will be there this course again
next year or next semester.
next semester.
Yeah, next semester this course that I'm not so sure of, but it should be there. It is there every year till December.
Ah, okay, okay. Because it is now it is live, but after some time it will they will give recorded, right?
Yeah, it will be offline. I think in YouTube also there is some recording of 2020 lectures.
So it is this is not live course, right? Means it is already recorded.
Yeah, this is a recorded course. Only this interaction is live, whatever we are
Ah,
doing.
yes, yes. That is the thing. So it will again come again, right?
Yeah.
Okay, okay, fine. Thank you very much.
Okay. Sure. Thank you. If there are no more questions, we'll stop here.